Okay, today we're going to talk about the next part of thermo, which is going to involve what's called Hess's law. Okay, and a law, again, is an observation of a pattern. And so we're going to be able to determine energy changes for whole reactions based on Hess's law. Now, if we go back just a little bit, H we defined as enthalpy a little bit earlier, and it's what we refer to as a state function. Now, I didn't talk too much about state functions. If you want to see kind of what that means, look on page 243 in your textbook. But more importantly, the important reason a state function counts, so to speak, is that the change in enthalpy is independent of the pathway. And that may not mean a whole lot right now, but what that means in solving problems is that for Hess's law, when going from a set of reactants to a set of products in any chemical reaction, we can look at the delta H, or the enthalpy, is the same whether it happens in one step or a series of steps. And so what this does is this allows us to calculate the delta H value for a chemical reaction. And as a reminder, one of the other things that's important for delta H is most of the time in chemistry, when we're finding enthalpy or delta H, we can set it equal to Q, or the heat lost or gained in a system. So that's kind of how we're able to do these calculations. Now, example 1, this is a graph first. This is the same overall reaction where you are starting with your reactants are nitrogen gas and oxygen gas, and it's undergoing a synthesis reaction or a combustion reaction because we have oxygen gas as a reactant, but to form nitrogen dioxide. And you can look at it as a two-step reaction, where the first step is you go from the diatomic nitrogen and diatomic oxygen, you get one molecule of nitrogen monoxide and still diatomic oxygen, and then in step 2 you go all the way to the 2 molecules of nitrogen dioxide. And so this is saying this first step would be an endothermic process that required the input of 180 kilojoules, and the second process would be an exothermic that allowed the release of negative 112 kilojoules, which got you a total endothermic process of 68 kilojoules. Over here, this is showing you exactly the same thing. If you look at the one-step reaction, we also can notice that the change is the same. So take-home message right here is that one step, 2 steps, however many steps it takes, if it's the same reaction, you get the same answer for the delta H. And so how would we solve a problem? Well, so here's the example of what I was talking about, where you have one step, and again, you have the positive endothermic, okay, meaning that heat is flowing into that system. You need 68 kilojoules for that to occur, or you can get the sum of 2 reactions, where the first reaction was endo, positive 180, second reaction was exo, negative 112. You simply add them together, and you get 68 kilojoules. Now you'll notice what we do is we cross off chemical substances or species that are exactly the same on both sides of the reaction. Okay, so since we have the nitrogen monoxide as a product and as a reactant, we cross them off, and if we add up what's left, just like we did with balancing redox, we get the net reaction. Okay, now here are some rules. Essentially what's going to happen is you're going to be given a whole bunch of reactions or equations, and you use those to get the final answer. And if a reaction has to be reversed, and the reason you would have to reverse it is if the chemical species you need is a reactant and you need it as a product, we reverse it. And this will make more sense when you see this. But if we reverse the reaction, we have to reverse the sign, because instead of it being exo, it would be endo, or instead of it being endo, it would be exo. And this, again, the sign tells us the direction of heat flow as constant pressure. Also, the magnitude of delta H is directly proportional to the quantities of the reactants and the products in the reaction. So it's an extensive property, meaning it does depend on how much is present. So if we have to multiply a reaction to get something to cancel out, we also have to multiply the delta H. And again, you'll see what that means, okay, which is that last statement that if coefficients are multiplied by an integer, the delta H must be multiplied in the same way. Alright, so let's do There you go, because delta H is an extensive property. So let's do a couple of samples. There we go. Alright, using the enthalpies of combustion. Now, what's going to happen is you're going to get a few different enthalpies of, we're going to talk about enthalpies of formation in the next section. You can have enthalpies of combustion. You also can have enthalpy of vaporization, which involves turning something into a gas. And a couple of other enthalpies, and we'll point those out as we go. But enthalpies of combustion for graphite is going to be negative 394 kilojoules per mole, and for diamond is negative 396. We want to find the delta H for the conversion of graphite to diamond. So the reaction, and they're both forms of carbon, so you've got graphite, carbon graphite solid converting to carbon diamond solid, and what's the delta H going to be? Okay, well they'd have to give you some more samples or some more information, and this is, just like it said on the last slide, this problem is worked out in more detail on page 258 of your textbook if you need a little bit more. Okay, so since we talked about the enthalpy of combustion, it means when we combust something, you know, what are we going to get? So if we combust graphite, our delta H is negative 394 kilojoules per mole, so it's exothermic, and our combustion of diamond is negative 396 kilojoules per mole, so it's also exothermic. Now, to get the desired overall equation that we originally wanted, because remember, we want to go from graphite to diamond, I have to reverse the second equation. So what that looks like is I still keep the first one exactly the same because I want graphite as a reactant, but I got to flip-flop the second one. And so what I did, you'll see it designated a few different ways, but by putting a negative sign out here, essentially what I'm saying is I've changed the sign. It was negative 396 up here. Since we flipped it around, it's now going to be positive 396 down here. Okay? Now the good news is that once you get it all lined up correctly, the math is very, very simple. And we get rid of the oxygen. We also get rid of the carbon dioxide, because they are on both sides of the equation. So for a summation, we end up with carbon graphite solid converting to carbon diamond solid. We simply add these two numbers together, and we get a final answer of 2 kilojoules per mole. And it is an endothermic process because it is positive. Okay, it really is that simple on the endo and exothermic when looking at the delta H's and determining the direction of something. Okay, one more sample. If you look on example 6.8 on page 259, okay, this time we want to find delta H for the synthesis reaction of diboron hexahydride, if I've named that correctly, or otherwise known as diborane. Okay, so there's a classic case of when some chemicals just have their own other name that may not follow the rules. But anyway, okay, here is the overall reaction. It's going to take 2 moles of boron, or 2 atoms of boron, combine it with 3 diatomic hydrogens, and we're going to get diborane over here on the other side. Now, what they would have had to have told you is they would have given you all these reactions, and you have to essentially manipulate them so that you have the boron and the hydrogen as reactants, you have the diborane as your product, and this is the only thing that you're left with at the end. Okay, you don't have everything else needs to be canceled out, so we got to figure out how to cancel out the oxygen and the waters on there, and also pay attention to the states. Okay, so how do we do that? Well, first of all, we want to pay attention to what needs to be on the reactants and the product side. So for the first one, the first reaction they gave us, we're going to keep exactly the same because we want boron as a reactant. So we're good on that one. Okay, the second reaction they gave us, they had the diborane as a reactant. So we went ahead and flipped this one around because we need diborane to be one of our products. And we also have to change the sign of the enthalpy given for that reaction. Okay, so originally it was negative 2035 kilojoules, so we've switched it and we've made it positive. Okay. Alright, then we have hydrogen, and here we go again with our fractional coefficients. It's just the way it is, we got to get used to it. We don't, on our equation predictions, we don't want to use fractions, but sometimes we'll see it on these. Okay, so the enthalpy associated with this reaction is going to be negative 286 kilojoules. And then we also have another water, primarily so that we can cancel out the other ones, that's going to be 44 kilojoules. Okay, so we now have, and one of the ways that I like to do this, and I did give us a whole nother slide, so I'll go ahead and bring this up on the next slide. But when I get here, what I like to figure out is what do I need to keep and what do I need to get rid of. Now remember, my overall net reaction, I want to keep the boron, okay, I want to keep the hydrogen, and I want to keep the diborane. Everything else needs to go away, okay, it needs to be canceled out. So that's essentially what this slide is telling you, except that I think I underlined it instead of highlighting it here. Okay, so that I've underlined again the boron, the hydrogen, and the diborane. These are the ones we want to keep. We just have to make sure that everything else cancels out. Okay, and in order to do that, we're going to have to multiply some things. And what do I mean by that? Well, for example, if you just look at, let's just isolate, the gaseous water that we need to get to cancel out. Well, in this reaction, there's 3 moles or 3 molecules of gaseous water as reactants. Down here, there's only 1. So chances are we're probably going to have to multiply this reaction by 3, which all that means is we also have to multiply the enthalpy by 3. Okay, and if we do that, then we also are probably going to have to multiply this one by 3, because now we're going to have to, since we're going to have 3 liquid waters, we're going to need to cancel out 3 liquid waters for this one, plus what will allow us to do is to cancel out the oxygens, because I've got 3 oxygens as products I have to cancel out. Here I have 3 halves, or 1 1/2, however you want to look at it, and if I multiply this by 3, that's also going to give me my other 1 1/2. Okay, so it's a little bit tedious, but final answer here, like I said, we need 3 hydrogens, we also need 3 waters. So what we need to do on this slide is to take the last 2 equations and multiply them by 3. So again, we're going to multiply all of the species by 3. We also are going to multiply the enthalpy values by 3. Okay, then we cross off all the things that we've canceled out. So we got rid of our oxygen, we got rid of our waters, we got rid of the additional compound with the boron and the oxygen in it, we got rid of our liquid water. So all we're left with is the original equation that we wanted, and then we just have to do all our math for our delta H. So we've got our negative 1273 plus, and I put the negative 2035 as a reminder that we had to flip it at the very beginning. We also have 3 times negative 286, 3 times 44, for a total delta H, or total enthalpy, of 36 kilojoules, which again would be an endothermic reaction because this value is positive. Okay, I hope that helps.